Okay, welcome everyone. We'll be shortly starting our next session. And in this session, we will work with graph data. So as usual, we should start with, let me just double check everything's okay. Everything's okay. We will start with starting Julia and Jupyter Notebook. So first thing we need to do is to start Julia and -- project makes sure that you tell Julia to activate your local project environment so that the packages that are installed are visible. Now we use iJulia package to load Jupyter Notebook, and now I spin up the notebook in the current working directory. So shortly the Jupyter Notebook will show up, and we go to day 3B, mining complex networks. So let me first start with the scope of the lecture. So what we will cover the following topics: how to work with graph data in Julia, how to do simple analysis of graph properties, and in particular, how to build a prediction model for node classification tasks. So maybe before I move forward, let me briefly explain what node classification task means. So first of all, what is a graph? Graph is a mathematical representation of networks, and the network consists of two types of objects. One type of objects, so-called nodes, are elements that are the backbone of the graph, and the other element are edges, and edges connect nodes. So for example, you can think of that in a social graph, for example, on Facebook or Twitter, nodes are users, and edges are information which two users, for example, know each other or exchange messages one with the other. And node classification task means that we assume, or we have information that each node has some feature like, for example, does this person, I don't know, like sports or like music, and we want to predict whether indeed what is the feature of this individual node. So for example, a user of a social network using information about the whole graph around this person. So for example, it's neighbors. Neighbors means other nodes, so other people connected to this person. Why it might make sense? It might make sense because we can expect that if we want to predict if I look like music, of course, it's worth to know how old I am or where I come from or what is my browsing history. But most likely, if I like something, my friends also might like things similar to me. So actually learning what my friends like might help predicting what I will like. And this is exactly the task that we are going to cover today. So let me start the notebook that we will work with. So this is the mining complex networks notebook. Now I click on it to open the notebook. So what graph we will work today in this class? We will work with so-called GitHub social network graph, which means that this is information about developers from June 2019 that were on GitHub. And if you have a graph, you always need to say how are nodes in this graph defined and how edges in this graph are defined. So in this case, nodes are developers with the condition that this developer has started at least 10 repositories on GitHub. And edges are mutual follower relationships between developers. So if I have two developers, first of all, I only look at developers who have started at least 10 repositories. Why? Because I want to focus, or let's call it active developers. So developers that are really active on GitHub. And the second thing, okay, how do I define edge? I define edge if developer A followed developer B and developer B followed developer A. So we can see that in this case, this edge is a mutual relationship. So we can say both A knows B and B knows A. And it will be important in our analysis, this assumption. Now, what is the task, the ultimate task that we will want to solve today? So for each developer, there is an information, what is the speciality of this developer. And this speciality for the purposes of this task is divided into two types. So either I am a front-end developer, so I'm doing web, I don't know, JavaScript, this kind of HTML, this kind of things, or I am a machine learning developer, so, you know, working with Julia, TensorFlow, or whatever language for doing advanced analytics. And our challenge will be the following: can we predict, if I give you some developer from this graph, I do not disclose you what type this developer is, but you can query me who are the friends of this developer. And the question is, can we predict, knowing the friends of this developer, if this developer is machine learning developer or a web developer? So maybe before we move forward, let us just, you know, try to predict what we expect. And it's not only because I want some interaction, but actually I want to stress this step because it's, in my opinion, fundamental in any data analysis task. So before you do any data modeling, it's very important to have some hypothesis what you expect. So either then data confirms it, and then, you know, you are reassured that what you thought is right, or if the data does not confirm it, it's very important that you think why you might have a discrepancy between your expectations and what data shows you. This is important because in many cases people do the project in data analytics that they start analyzing the data, see something, and then, you know, try to, you know, think of, okay, if I see this data, let's create a mental model why it happened. It's okay, but it's often more useful to think of such things upfront, so that you are not biased by what you see in the data. So that, you know, it's better to think a bit about the problem before going to the computer with pen and paper, maybe. Okay, so what would be your expectations? If I look at friends of some developer, what would be the expectation when, for example, let me see. Let me ask the following question. I look at developer, I know the friends of this developer. How would I possibly be able to predict if this developer is machine learning or web developer? What would be the things that could predict this? Yeah, so this is a natural thing. So I say, okay, I assume you mean the following. If I have a lot of machine learning friends and few web developer friends, then most likely I am a machine learning expert. And similarly, if I have a lot of web friends and a few machine learning friends, I'm most likely web developer. So this is a natural approach, and this is also what I would expect. And this is the way how we want to analyze this data. So what we will want to do is for every developer count how many web friends this developer has, how many machine learning developers friends this developer has, and is indeed this an indicative feature helping me to understand what is the kind of the developer we see. Okay, so let us move forward and try doing this analysis. So first, we load several packages. And as I have explained you earlier, what I can do nicely, I can highlight several cells and then run them. We can see with the asterisk which cells are still to be executed. We can see with this field red circle that the Julia server is still doing computations, and now we are done. So let me discuss briefly what are the packages that we will use. So categorical arrays is a package for working with categorical data. So data that can be thought of as having a finite set of fixed values. So for example, I don't know, red, blue, green as a color is categorical data, or for example, categorical data would be a grade in a course. So if the grade is in a course is A plus A, B plus B, etc., this is a finite set of fixed labels. So this is categorical data. Then CSV package is used for loading and saving data in CSV format, so comma separated values. Data frames meta we already saw in the first day of the course is for working with data frames. GLM is package also, you know, this is for creating linear regression models. Graphs is a new package. This is a package in Julia for working with graphs, which is probably pretty easy to guess. Then we have a plots package that you already know is for plotting, and two packages we already also use, statsbase and statistics, providing various statistical functions. So what we start with, we will read the source file. The source file name is music-git edges CSV. We can quickly get a peek at this file. As you can see, in the first row, there is a header, so we can see that there are two columns, ID1 and ID2, and we have then numbers that represent developer number that are comma separated, which means that, for example, we see that developer number 0 is connected to developer number 23,977. So this is the file that gives me information about edges of the of this data frame of this graph, and because this is a CSV file, we can easily read it into a data frame, for which I use CSV read function. The first argument is file name, and the second argument is the target, the storage type. So in what type of object I want to store the data. In this case, I want to store the data in a data frame object. So I say, read me in this file into a data frame. And if I run this command, we will see that we have edges nicely, edge information nicely read into a data frame. So we can see that we have almost 300,000 edges in this data set, and each of the one row is information about one edge. Here, what is important to remember that we can see that mostly those numbers are from smaller number to larger number, but not always. Sometimes it's from larger number to smaller number. But we remember that in our case, it doesn't matter. Why? Because we said that edge is a mutual relationship. So actually, if I write 1, 2, it's the same as writing 2, 1, because this is a mutual relationship. So now we have read in the edge information for our graph. The second information that we will want is to get information about the developers. And the information about developers is in the second file, which is called music-git target CSV, and it has 3 columns: ID, so then number of the developer. The name of the developer, we will not use it, but it's just there. For example, I don't know. No, we cannot look it here, but we could look for some developer in this yeah, here. Okay, for example, I can look for Stefan Karpiński. Stefan Karpiński is one of the creators of Julia, and we can see that he is in this data set under number 1358, and his label is 1, which means that this developer, one of the creators of Julia, is of type ML target 1, which means he is flagged as machine learning developer. So Stefan Karpiński in this data frame, one of the creators of Julia, is seen as a machine learning developer, not a web developer. So let us read in this data set again to a data frame. So the structure is the same. And we see that we have 37,700 developers in our database. Now we can have a look at the structure of those data sets. So to have a look at structure of this data set, we can use the describe function. We already had used it before, but now what we additionally do, we provide which functions we want to be applied to our data set. So I want minimum, maximum, mean, number of missing values, and element type. And I get nice information about this. And we can see that the minimum number is 0 and maximum number overall is 37,699, which is 1 less than the number of rows in the second data frame, which is expected because we see that developers use numbering starting with 0, not with 1. So if we are starting with 0, we end up with 1 less. We can also have a look at the second data frame, which is classes DF, and again we get information that okay, developer numbers are again in the same range, which is good, which means that the data sets are consistent. For example, we do not have edges that do not point at any developer. And most likely we will shortly check it. We don't have a situation that I have a developer that has no edges attached to it, but we don't know it yet, but it seems that it should be the case. But what is interesting is one of the informations is the mean of the ML target column. This mean is around 25%. What does it mean that ML target column, in which 0 means web developer and 1 means machine learning developer, what does it mean if we see that the mean of this column is around 25%? How would it be interpreted? So a mean of binary column like this. Yeah, exactly. So we can see that actually there are around 3 times more web developers than machine learning developers. Why 3 times more? Because 1 in 4 roughly is machine learning developer, which means 3 in 4 is web developer. So in this data set, it is a so-called unbalanced data set because one of the classes is more frequent than the other class. And we already start thinking about our initial hypothesis. Why? Because we said we expect that if I have many web developer friends, probably I'm a web developer. If I have many machine learning friends, I am most likely machine learning developer. And probably this still holds. But what change to our thinking or our expectations might come when we see that actually there are much fewer machine learning developers than web developers? What would you say that could change in our initial hypothesis? Exactly. So for example, even if I see that I have few web developers friends, probably it's not a super strong signal because there are many web developers anyway in the database. But on the other hand, probably if I even see a few machine learning developers that are my friends, this is a much stronger signal because those are much more rare. Yes, so we can expect that there will be imbalance in the strength of the signal of having one web developer and one machine learning developer friend. And again, this is something that we will check in our analysis. But before we move forward, we need to fix our data. And this is typically called data preprocessing or data cleaning stage. So what do we need to do? We need to do one small correction in the data. So as it was discussed in earlier lectures, Julia uses a so-called one-based indexing, which means that if we have arrays, if we have any data structures, typically indexing of those arrays and structures, just like in mathematics, starts with 1, not with 0. This is similar to R, for example, or MATLAB, but is different in comparison to, for example, Python, because in Python we start counting with 0, not with 1. So most likely this data set originally was prepared for analysis in Python, so this is probably why its numbering was started with 0, but we need to fix it so to have one-based indexing in our data set because it will be easier to later work with it in Julia. So how do we do it? Well, it is quite easy. I just need to add 1 to every column that represents developer ID number. So because in edges data frame, every column is essentially a developer ID because I have 2 columns. Both columns are developers IDs. So I need to add 1 to all elements of edges data frame. So I simply write plus equals 1. I need to do this dot, to use the dot. We have seen the dot already. This dot means that I want to broadcast this operation. So as Professor Edelman said, it is like point. So for each point, so for each element of the collection on this site, so in this case, this is a data frame, I say I want to add 1 to each element within this collection. So that's why I use this dot here. So I add 1 to every element of the data frame. And if I run this operation, we can see that indeed now where we had 0, we have 1, when we have 1, we have 2, etc. Yes, so we can see that we started at 0, 1, 1, 1, 1. Now we have 0, 2, 2, 2, 2, etc. So indeed we have updated our data frame by incrementing every of its elements by 1. But in the second data frame, I do not want to update whole data frame because it has also other columns that are not IDs. I want to only increment the ID column of our data frame. So this is equally easy. If I want to update only one column, as we remember, using after the dot, I can write a column name. So I just write classes df ID and again dot plus 1. Plus equals 1, which means I increment only a single column by 1. Again, pretty simple. Now I incremented this column by 1, and now I have both data frames using one-based indexing. So is this clear? Okay, so we can move forward. So now the crucial step is to transform this data into a graph form, because currently we have data that is stored in tabular format because this was the way the source data was stored. But I want to create a graph from this data and do some initial inspection of this data. So how do I do this? So I start with creation of the graph, and I create a so-called simple graph. Simple graph means that this is an undirected graph and also that it has two more properties. Simple graph means that there are no so-called self loops. So I am not a friend of myself, which in this interpretation that we gave makes little sense, that because I cannot follow myself technically. And the second is that simple graph means that there are no multi-edges. So there is not a situation that we have the same edge twice. And again, for example, in road network, it could be possible that I say, okay, between 2 points, there are 2 roads that I can take to get from A to B. So, but again, in our interpretation, it makes no sense. We say just, we are connected, so there is always a single edge connecting me. So this is exactly what is the definition of simple graph. Again, 3 conditions: undirected, no self loops, and no multiple edges. Such a structure is called simple graph, and that's why we in this our example we will use a simple graph. Of course, we can use other types of graphs in Julia, but this is the simplest one. So actually, it's nice because the graph is simple, so it is simple to work with it. But this name simple is not because it's simple to work with, but because this is a mathematical definition of a graph that is simple. And what we need to pass to this graph is how many nodes I want to have in this graph, and number of nodes is number of rows in our classes data frame. So just simply number of developers. And if I create this, I get that this graph has indeed 37,700 nodes, so developers, but unfortunately now it has 0 edges, which means, okay, I have a graph, but this graph does not know yet who likes whom or who follows who. So I need now to add to this data structure information about who follows whom. And this is pretty easy to do in Julia. So what I need to do, I need to iterate the edges data frame. And let's remind ourselves what is this data frame. This data frame has many rows. One row represents one edge in our data frame, and this row has 2 elements. Yes, for example, 1 and 23,978. So what I do, I want to iterate rows of this data frame and extract out both ends of the edge. So I call those ends, yes?
Directed graph enough here, because if I follow you, does it mean that you follow me? Because this undirected graph is kind of assuming this, yeah, having just one edge, that we do not distinguish who is following who.
Yes, why? Because as we said initially, the edge is created only if there is a mutual follower relationship. So I create an edge only if A follows B and B follows A. So if there is one-way relationship, I say no edge. So this is not a relationship. But it is a very valid question. If the source data were defined in a different way, we would have a so-called directed graph, which is also supported. It would be a digraph, DI for directed graph. It would be a bit different data structure, also supported, but in this case, source data is undirected graph because I create an edge only if the relationship is two-way. But actually, So it should be SRC. This is typo, but it does not matter. I just say, okay, I iterate each row of my data frame, and because I know that row has 2 elements, I just extract those 2 elements and give them name SRC and DST. And here is a relevant thing related to the question from the audience, that I say source and destination, but in this case, actually, I could reverse it or just say it's AB or XY or whatever, because it doesn't really matter who is the source and who is the destination. But you know, by convenience, usually you say that one end of the edge is source and the other is destination, but you just remember whether this is indeed one-way relationship or two-way relationship. And what I do, I add to my graph this edge, whose one end is SRC and the other end is DST. So who can tell me why do I have a bank here? Who does remember from earlier classes? Yeah, exactly. And what is modified here? Yes, exactly. The graph. I add this edge to this GH object. So I modify GH object, which means this name, exactly as you have said, signals to me, warning, I am going to change something you passed to me. In this case, GH, and I think, do I want it? Well, I say, yeah, actually, this is the only reason why I do it. So in this case, it makes sense. But again, I am notified of kind of operation that is going to happen, but in this case, this is intended. So I run this, and as you saw, it is almost instant to add those edges. So, you know, adding 300,000 edges is a super fast operation. Maybe let me show you how to check the time of operation. It was already shown earlier. If I add time before some command, I can see how long it took. So we can see that creating a graph takes around 1/1000th of a second. And now we can also check how long it takes to add these 300,000 edges to this graph. And we can see that it's like 2/10 of a second. So it's really pretty fast, which why it's important, because we see that this graphs library in Julia is ready to work with really large graphs. So, you know, if adding edges, 300,000 edges took us around, 2/10 of a second, we can see that, of course, it would take us more time, but mentally working with billions of columns, of edges, of course, it would be longer, but it is imaginable. So it would not be days to process it, but rather seconds. So that's why, and I could also make this operation faster, but for 300,000 edges, it's so fast that I didn't need to optimize it further. So this is, yes? Yeah. So this adding this source and destination, I could do it from any source. So for example, let me, yeah. So someone could ask, because you commented, maybe let me show it, if we can do this process faster. So I will now write a bit more advanced code that will do the same operation faster. I will not explain all the details, but just focus on speed. Okay, and now I do exactly the same. I have rewritten this a bit, and Now we can see that only with small changes, I am already around 2 times faster. And still this could be even yet optimized, yes? Number of columns? No, so for edges, it's like 2 columns. So, you know, it's like... No, so this is here the issue is not about number of columns, because the zip function, just to show you what zip function does. So let me define x. Yes. So as you can see, if I zip something, it works like a zipper. Yes. So first, second, third. Yes, this is a zip function. But if you ask about performance difference, so the performance difference is the major reason is number of allocations. So here you can see that I had 4 million allocations. Here I had 2 million allocations. And the difference is, and this is a bit more advanced topic, so I didn't plan to cover it in detail, but if someone is interested, you can write me an email, that I have turned with this let and with this zip the code into a so-called type stable code. So when I'm running this operation, Julia is not aware of types of data. So it runs in a so-called interpreter mode. It must dynamically check the type of data that I am working with. While this let operation and this zip allows me to pass to the Julia compiler information about types of variables. And if Julia interpreter gets information about types of variables, then it can optimize the code better. This was something that Przemysław was showing earlier with this code analysis that Julia generates. So, this twofold speedup is just because I rewritten a code a bit to make it more compiler friendly. And why I have shown this, because in this case, everyone would agree that it doesn't really matter because this is fast enough. But I am showing this for the following reason, that this is the type of code that like many people naturally write when porting some code from Python or from R to Julia. And sometimes people say, okay, we can see speed up, but this speed up is not as big as we would expect. And usually the reason is that to get the full benefit of Julia, you need to restructure your code a bit to take advantage of Julia's compiler capabilities. Why? Because Julia has some certain patterns where if you use those patterns, your code will be fast. But of course, in any language, you can write a slow code. Yes, so even if in Julia, although in general it is fast, if you don't write your code correctly, it will be not so fast. So this is just an example that small changes in the code can have significant performance impacts, and that when you learn Julia, especially if some operation is not as fast as you would expect, you should make sure that you do not do some anti-patterns that shouldn't be used in Julia. Okay, so let us check our graph. So our our graph has 37,700 nodes, and now we can see that it has and now it is important, 289,003 edges. Now I go back to my original data frame with edges, and we can see that I get exactly the same number. What does it mean? That I have exactly the same number of edges in my graph as the number of rows in my source data frame. Is it a good information or bad information? Maybe the first question. Exactly, this is a good information. Why? Because I can see that every row in my data frame ended up to be an edge in a graph, which means in particular that my source data didn't have self loops and didn't have duplicate edges. So my source data was clean. Because I earlier told you that it seems it is clean, but actually after running this operation, let's call it for free, get additional reassurance that indeed the data was clean and correct. Because if it were incorrect, I either would get an error or I would get less edges than rows in the data frame. So this is also, as a side benefit, a way to check that the data indeed was as expected. So additionally, I check with NE number of edges in a data frame. I can check with NV number of vertices in my graph. But again, it is this is as expected, and I will do one additional check. This additional check is one of the many features of graphs. So in in graphs.jl library, I have many. iGraph is a popular graph package for Python and R. So in graphs.jl library, I have many functions that can help me to check properties of the graph. And one of those properties of the graph is finding so-called connected components of a graph. If you hear the name connected components, what would be your guess? What connected components of the graph would be? Maybe, of course, someone of you are experts in graph theory, so you just know the definition. But if you've never heard the definition, what would you think? If I ask for connected components of the graph, what information I am looking for? Just intuitive guess. Yeah, exactly. So I'm asking the following. If I can divide my graph into smaller graphs so that each smaller graph has a property that each node can be reached from every other node. So in this case, if I run connected components and I get information that I get one big connected component consisting of all nodes of my graph, what does this mean? Exactly. So maybe they are not connected directly, but essentially everyone is connected to everyone either directly or indirectly, right? So we can see that our graph has a nice property that every node can be reached through any other node, which means that we can say that in our GitHub developers community, it is well connected in a sense. So it means that, okay, if I'm looking for to get, to communicate with some other developer, I will be always able to find a chain of friends who will eventually lead me to the person I want to meet. So actually, I can ask for diameter of this graph, and it will take a bit longer to compute. And the diameter of the graph will tell me what is the length of the longest path in this graph. So let's see how long it takes. It is a bit more complex operation. So now we are trying to understand because we already know that each path in this graph is every two nodes are reachable from each other, that I can calculate the diameter of the graph. So what is the length of this longest path in my graph? So this computation will take a bit of time because my graph is pretty big. So let me discuss what we will do next. So what we will do next, we will want to analyze the And if it doesn't finish too fast because I am at the same time streaming, which also always slows down things, maybe I will interrupt this operation. Okay. No, it's, you always need to learn something. So, okay, so what do you do if I'm stuck with a long operation? Okay, so first of all, I do restart. I'm now restarting the kernel, which means that now I am starting all my computations anew. Now it's okay. It's always important to know how to recover from a problem. So I started a very long operation. It took longer than I expected because my computer is doing now a lot of other things. So and now I just restarted the kernel. And a nice thing about GitHub Notebook is that now I can run everything up to this point. So what I do cell, and I do run all above. So I run all cells above this connected components cell. So we can see that now all those cells are with the asterisk, and they will be run again to get me back to the state of the notebook where I am currently. And actually, this pattern of using notebook is quite important. So what I mean by the pattern? So because notebooks in general in Jupyter can be executed non-linearly. So I can execute any cell at any time. This is allowed and possible. Let's just rerun. Everything is okay. This is allowed and possible, but this should never be done. Don't ever do this, because this will lead to very hard to catch bugs. Even though Jupyter Notebook allows you to, execute any cell anytime, this is something you should never do, because if maybe now you are a student, but if you go to a job as a data scientist, and you will have to work with ML ops engineers that then move your notebooks to production, they are not going to like you if you have your notebooks in a way that you don't execute all the cells in sequence. So although Jupyter Notebook allows this, always make sure to execute everything is in sequence. So for exactly this reason, although I could interrupt just a single operation, I preferred just to kill the notebook and recompute everything to be sure that I am in a proper state of the notebook, because I don't want any problems during my lecture this time. And just like if you are in production, you don't want any problems either. Okay, so we know that we have this one connected component. So what we will want to compute, as you remember, how many web developers and machine learning developers friends I have. And this is connected to a concept of a degree of node. So what is a degree of node? Degree of node is in general number of its neighbors. And degree as defined by default means any neighbors. So for now, we are not concerned whether this is a machine learning or web developer neighbor. It's just any neighbor. So to get a list of degrees of nodes, you use a degree function. So if I run a degree function, I get, I already ran it, I get number of friends of a given node. So we can see, for example, that developer 1 has only 1 friend, second has 8 friends. There is some developer that has 215 friends. So what do you think, given the data that we already see, what is the minimum degree in our graph? 1. Why 1? Yes. Exactly. So I already see 1, like here and here, and I know I cannot get 0, because then I wouldn't have this connected component as a single component. I would have at least two components in my graph. So having both information, parts of information, I know that minimum degree is 1. And what is the maximum degree in my graph? What is the value that I'm sure it will not be higher than this value? We don't know how big it will be because we can see that it's at least 215, but maybe it's bigger. But can you put an upper limit on the degree of a node? Exactly, because the most I can have, I can be connected to everyone, right? So if I were connected to everyone, my degree would be 37,699. So this is the upper bound. But actually, we will just check what is the lower and upper limit. But first, let us add this degree information to our data frame so that I can nicely keep this data in a tabular format. So I create a deg column, so degree, to just add the degrees to each developer. And now I can describe my column. So as earlier I have shown that you can describe a data frame like this. So now I have described the data frame, but in a similar way I can just describe a single column. So if I describe a single column, I get summary statistics of this column. So indeed I can see that minimum degree is 1, mean degree is around 15, median of degree is 6, and maximum degree is around 9,500. Yes, so indeed there are some developers that are really popular. We can check this by doing a histogram. And what do we expect to see in this histogram? What do you think? Very long tail. Yeah. Exactly. We could even see that we almost do not see anything, right? Because there is like everything is concentrated here and a few values here. So just as a quick check, we could take a logarithm. Now I do not need log 1p because my minimum is 1. So I know that after this, my minimum will be 0. And we can see that even after taking the logarithm, I have a long tail, but it's not that long as it were before, right? So again, still a long tail, but not super long, because earlier it was extremely long. So such graphs that have such a long right tail of degree distribution, and this is something you can check statistically. I will not cover this today, but typically they can be verified to follow a so-called power law degree distribution. And this power law degree distribution is a popular, very often encountered in social networks. So for example, if you have, I don't know, Facebook, social graph, and different kinds of this graph, you see exactly the same. So most of people have a very few friends, but some of the people have extremely many friends. So this long right tail is a very frequent feature of social graphs. And our GitHub developer graph also exhibits it. Okay, so we see that this is a highly skewed distribution. So now, as a warm-up, I will ask you the following question, and you can treat it as a kind of a puzzle. So we can see here that mean degree in this graph is 15. What does it mean? It means that if I pick a random node in this graph, like uniformly unrandom, I say, okay, give me some node, and I am to predict what will be the degree of this node, then the prediction is, on average, I will see a node of degree around 15. This is the mean degree. But now a question I can ask is the following. Okay, but what if I do not pick this node at random, but I do a bit different process? I start in some node on the graph, and I start walking on this graph randomly. I walk on this graph randomly, which means I am in some node. I randomly, uniformly at random, pick one of its friends, and I repeat this process. So this is kind of the process that, for example, you can say, okay, I go to a website and click on a link randomly of the links on the website. Then again, on this second website, I again click on a link, and so on and so forth. So I randomly walk around a graph. So is that process clear? We want to simulate? Okay, and the question to you will be the following. Actually, there are two questions related. So if I do not pick nodes at random, but rather I walk through friends of friends, etc., what in this case will be average degree of a visited node in the long run? Because if I visited nodes randomly, uniformly at random, I would see an average 15. But what if I visit them not uniformly at random, but in a process that I visit a friend of a friend? One thing we already know is that eventually I will visit every node. Why I will eventually visit every node? Because the graph has one huge connected component. So eventually I will visit every node. But what would we, again, before we do anything, think? And what do we think? Will the average degree of a visited node in this process be larger or smaller than the average degree of node picked at random? Why?
Which is kind of like, then you can go to someone like one of their friends, but their friends will have like a median of 6 connections, or they could even have one. So like in the worst case where you have one, then you're immediately drawn back to 9,458. And even in the median case, there's like 1 in 6 chance you'll go back to the T.
Exactly. So essentially what you say is that the probability of visiting a node in the long run is not uniform, right? And which nodes do you think are visited more often? High degree nodes will be visited more often. So this is exactly, now we will learn in two ways how to verify this. So first way to verify this is by simulation. And simulation is a pretty powerful computational technique where we do not do any computations, using formulas, but we say, okay, I don't know how to answer this question, but I can write a code that will just run and answer the question for me, so that I can see if my hypothesis is true. So this is exactly what we will do first. So I3A create a function that is called travel. Oh, and by the way, doing simulations is one of the strongest advantages of using Julia. So, there are many applications where Julia is nice, but actually, if you need to do a simulation, indeed, this is the area where Julia is really, really a good language to use, because you can do those simulations very fast. So how do I design this simulation? So the simulation function will be called travel. I pass 3 arguments to it. The first argument, gh, is my graph, gh for GitHub. The second I is the starting point of my simulation, and really I don't care where I start, because we will run this simulation for a long time, so the starting point does not matter, and we remember that I will eventually reach every node. And the third argument is steps. So for how long I want to run this simulation. And how does this function work? So dex variable will keep me the list of visited nodes, so the list of degrees of visited nodes. So I will just collect what was the degree of the node that I visited. So initially, of course, I visit node number I, so I just store the degree of this node number I in my list. And the second vector that I will use is visits. So initially I fill this vector with zeros because I say I visited only the first, I have not visited any node yet. But then I say, okay, but I'm visiting now node I, so I increase the number of visits to node I by 1. So eventually what I will return from this function is two things: dex, which will be a list of degrees of nodes that I have visited, and vector visits, which will tell me how many times I have visited each individual node. And how do I run the simulation? Well, I run it for steps times. So this is just a for loop that I run from 1 to steps iterations. And in each iteration, I randomly pick a neighbor of my node and I just move to it. So I becomes one random neighbor of I. And then to degrees, I push. So I add additional element that is degree. So at the end of the dex vector, I add additional degree that I just visited. And second, I record that I visited this additional I element one more time. Is it clear what I do? So after I run this simulation, I will get two vectors again. One, list of degrees of nodes that I have visited, and second, how many times I have visited each individual node. So now let me first of all define this function, and then let me run this function. So I run this function. Let us check how long it runs. It ran around 1 second, under 1 second. And we see that I ran it 10 million times, because 10 to the power of 7. So I ran it 10 million times and it's under a second. So again, it is pretty efficient. And I now can check this dex vector and visits vector. So first of all, I check dex vector, and mean of dex vector is 440. Well, compared to 15, it is much, much bigger. So actually, it seems that your intuition was correct, because it's indeed much bigger than just taking the mean. For sure, it seems that I visit high degree nodes more often than low degree nodes. But now let us think of how much often do I see low degree nodes than high degree nodes? What would you guess? To what will be the frequency of visits to a node proportional? What do you mean? Wait. So it means this 29. Yes, I know, but I mean, if I have a low degree node and a high degree, for example, I have a node of degree 1 and I have a node of degree 10. How many times more often do you think the node of degree 10 will be visited than the node of degree 1? 10 times? Good guess. Indeed, as we will shortly show, indeed, the frequency of visits is exactly proportional to the node degree. So it means that node of degree 1 is visited almost 10,000 times less frequently than the node of degree this highest degree, which was around 9,500. And because we have just checked that the distribution of our data had this long tail, which means that actually most of the time we just visit this super heavy node, right? So, first of all, let us check by verifying mean if this is the case. And this is in Julia super easy, because in Julia I can calculate something that is called weighted mean, because this is what we need. I want to calculate the mean of degree but weighted by the frequency of visits. And we just said that the frequency of visits is proportional to degrees. So what I do, I calculate mean degree, but not unweighted, because my process is not sampling at random uniformly, but I'm sampling at random, but with weight proportional to degree. So in Julia, I just say, okay, I want a mean of degree, but with weights proportional to degree. And if I compute this, I get that is 441, which is almost the same that we got here. Why is it almost the same and not exactly the same? What do you think? Why is it so? Why is this number not exactly the same as this number? Exactly. We have a variance. So because Julia is fast, let's say, okay, I don't do 10 million, but 100 million times. 100 million times will be a bit slower. I expect it to be a bit below 10 seconds. And now I did the timing, so it's not, yeah, it's a bit below 10 seconds, but it's now should be more accurate. And we can see that indeed this number is closer to this. So actually now it's only 2/10 of difference between those two numbers. So indeed, by increasing the sample size, I have decreased the variance of the estimator. So I am much closer to the exact value. And let's see. So this was our guess that weights would be proportional to the degree. But actually, we can check it. Why? Because first of all, I can compute the correlation of those two values. And if I check the correlation, this correlation is almost 1. So indeed, it means that those two values are super correlated linearly. And also, I can rerun now I run the linear regression, as Mateusz has taught you in the class on linear regression. And we can see that indeed the free term is almost 0 and almost everything is, so intercept is almost 0 and the only thing is slope. So actually number of visits is just a direct, it has a direct linear relationship with the degree. So of course this value is not 0, again, as you have said, because it's a random process, so it will not be 0, but this value in relationship to this value, we see that it is essentially 0. So we have really a relationship number of visits equals alpha times degree. Yes, so this is a linear relationship proportional, which means that indeed we have now by simulation verified that this is indeed the case. But verification by simulation, as you just mentioned, has one drawback. It's a random process. So can we do it better? Yes, we can. We can, instead of doing this by simulation, which is random, I can verify the same fact using numerical computing. And again, numerical algorithms is the second super big strength of Julia. So one is simulation, and random simulation in particular, very big and strong point of Julia. The other strong point is numerical simulation. So what we will do, we will first define an object that is called adjacency matrix. So what is an adjacency matrix? Here we unfortunately cannot see it because it's a very big matrix. It's a matrix that whose both dimensions are the number of vertices, but we can pick into it, for example, first 10 elements here and here. And here we can see that, okay, it's all zeros. So let us try picking 0 entries. Okay, because so we can see, okay, if we take 100 nodes, we can see that I have 4 dots. So 4 dots are the edges. So if I have edge from I to J, I have a dot here. And why those dots are symmetric? Because if I have an edge from I to J, I have an edge from J to I. So we have now an adjacency matrix, which means it has 0 if there is no edge between I and J, and 1 if there is an edge between them. So now we have a very important vector to define. I call this vector travel probability. What does it mean? It means that we said if I move out from some node, I randomly pick one of the neighbors. So I need to ask myself, okay, so what is the probability of visiting each individual neighbor? The answer is it's easy. It's 1/degree. So if I have one neighbor, like for example in the first node case, I will for sure visit only this one neighbor. The second node has 8 neighbors, which means that I visit each neighbor with probability of 1/8, and so on and so forth. Yes, so is this clear what travel probability means? And now we go to the most difficult part of today's lecture. Now I transform my adjacency matrix by this travel probability. So how do I do it? Yes?
So this is like Markov chains.
Yes, so now the TM is transition matrix, and this is exactly transition matrix of a Markov chain for people who know Markov chains. So what I want to do, I want to create from adjacency matrix a transition matrix. Again, for people who know Markov chains, this is Markov chain transition matrix. But what does this operation do? This is crucial. If I multiply such a matrix with a dot product, this dot here, I don't mean dot product, but dot and then product, I mean multiplication, then I multiply each row of, each column of this matrix by this travel probability. But what does it mean? That this TM, so transition matrix, will have the following property. If I calculate sum of row 1 of TM, what sum it will be? 1. If I calculate sum of row 2, what do I expect? 1. Row 3, 1, and so on and so forth. So now I see that in each row of my matrix, everything adds up to 1. And this relates to the question by Mateusz. That's why we call it transition matrix, because in each row I have transition probabilities from my current state to my future state, in the state in the next step. And now the most important thing that we will do is the following. Now we will not do a stochastic process, but rather we will do a process that is deterministic. I say the following. Start with ones, which means initially I put one agent in each node. So initially there is one agent in each node. And now I say, okay, multiply this vector of one agent by transition matrix. And if I do this multiplication, if someone does not know it, I recommend you to read a bit about those transition matrices, but we can see that after this multiplication, I will get an expected value of number of agents in the next step. I normalize it by sum so that in general I get the distribution also adding up to 1. So after one such step, I say initially all agents were distributed uniformly. In every node, it was with the same proportion. But now I say, okay, after one step, I expect that those nodes that have higher probability of ending up will have a bit more agents in expectations than those who have lower probability. And now what I do, I repeat that process many times. So by default, I will repeat it 1,000 times. And here we won't prove it. This algorithm is called power iteration method. That's why I call this function powiter. You can prove it that it will converge to a so-called stationary distribution. So in the end of this process, I will get a vector. So vector X will have deterministically, as opposed to earlier randomly, the distribution of probability of being in a given node. So let us run it. And if I run this power iteration algorithm, I get some numbers. And now what is important that okay, those numbers are small. What will be the sum of stationary probabilities? You guessed right, or knew, not guessed. So the sum of stationary probabilities is 1, but those probabilities are quite small. But what I can do, I can do the following. I can take my degrees and divide them by their sum. So then I also get the vector, row vector that has 1. And if I do this, we can see that those are exactly or almost exactly the same values. Actually, if I take a difference of those two values here and compute their extrema, we can see that this is a super small number, and 10 to the power of minus 15 is the numerical precision of floating point operations. So we can see that up to the precision of the computations, we get exactly the same result. So by using power iteration method, now it was not a random process that just, okay, it already ensured us that things are okay, but we were not, numerically sure because it was some randomness. Here, without randomness, we see that we get exactly the same results. So numerically, we have confirmed that indeed probability of visiting a node is proportional to its degree. So before we move forward, maybe you can tell me why this finding is important. So why is it okay? We have learned that if you travel around a network, you are more likely to visit high degree nodes. But why is it important, do you think? Why this, for example, if you are a business, why would it be relevant to you to know that pretty fast I will reach those high degree nodes when I randomly travel a network? Is it important, you think, or not? Why? Yeah, it seems it's important, but why? So I can give a short answer, but this justifies why celebrities in social media get so much money. Because as we can see, everyone in the network, if celebrity has degree high enough, will reach this celebrity pretty fast. So if celebrity promotes something, we indeed know, and social networks have this long right tail, exactly as our data, which means that almost everyone, if even randomly surfing a network, will eventually hit this celebrity. So that's why brands pay a lot of money to them to promote their things, because indeed they are quite likely to be hit. On the other hand, if you are a non-celebrity, your probability of being visited by some random network surfer is so low that most likely no one will want to pay you for your content, because, well, it's not that they don't like it or they don't like you, but simply, you are not visited frequently enough to justify it. So it's a super important finding in terms of making business on the web. And the other thing is, so this is like a finding in business, but this is not everything. So we discussed here this power iteration algorithm for undirected graph, and we have shown that random surfing over network gives us the result proportional to the degree of the node. But actually a small modification of this approach and generalizing it to a directed graph, so what Mateusz was asking earlier, led to one of the most successful businesses of our current, global corporation state. So which business do you think was built upon this algorithm that we have just shown? Which?
530.
Yeah, but which company? Yeah, exactly. So Google, so initial algorithm for Google for doing web search used algorithm that is called PageRank, and PageRank is adaptation or a variant of what we have just seen, but for directed graphs and with a bit of modification. This bit of modification is exactly because directed graph do not have to have this one big component. So you have to take into account that you cannot reach everything from everywhere. But in general, web search was exactly this, which meant, if you currently, of course, Google's algorithm is much more complex. But the initial idea was, if you ask about something, we give you the answer that has higher ranking in terms of probability of being visited, exactly as we discussed it today. So it's not only why celebrities get those money, but it's also how Google builds business. So if you knew this 30 years ago, you could be rich. Okay. So maybe the other task I will show you could make you rich in the future if money is what you seek, because there are other things that people can look for in life, but probably money does not hurt. Okay, so the other task we will discuss is this prediction of type based on types of my neighbor. So what we need first to understand how I can iterate edges of the graph, and this is pretty simple. We have a function edges that will feed me, just like each row was returning each row of a data frame, exactly the same way edges returns me each edge of the graph. And for example, if we want to see a first edge of the graph, it's 1 to this 23,978. We remember that this was this first edge. And if I check the structure of this edge with dump, we can see that it has exactly this SRC and DST names, and that's why I used those names also earlier. Although we remember that it's in undirected edge. And I can access those edges with SRC and DST. So now we write again a bit more complex function, but hopefully not super complex, that will compute number of web developer and machine learning friends of each node. So how do we do this? So I need to pass 2 arguments to this function. So my graph and the list of classes of each developer. So class is either 0 for web or 1 for machine learning. And initially, I say that my degree in terms of machine learning friends is 0 for every node and the same for web. Initially, I don't know any web developers. Clear? Okay. And I want those to be integers. So I'm counting the values. And now I iterate all edges here. And what do I say? For each edge, I call it AB. And I say, okay, if developer B is machine learner, this means that developer A has 1 more machine learning friend. Otherwise, developer A has 1 more web friend, because if it's not machine learning, it means it's web. But it's also the other way. So for developer B, I say is this a machine? If A is machine learning, is yes, then for developer B, I increase machine learning by 1, and otherwise for developer B, I increase number of web friends of B by 1. Yes, is it clear? So in this way, by iterating all edges, I get the number of machine learning and web friends of each edge. Okay, and I can run this and add 2 more columns to my data frame, deg ML and deg web. And maybe one more comment. Let us check how fast this runs. And as you can see, it runs super fast. So again, we can see one of the big benefits of Julia, that even we can freely use for loops. Those for loops will be really fast. So again, this is like super fast. So even if we had 1000 more edges in the graph, it would be only a few seconds to run this computation. So maybe let's describe our data frame and see what we learn. Okay, so first of all, we see that on the average, we had 15. On the average, each developer has 15 neighbors. But out of those 15 neighbors, on the average, only 2 are machine learning neighbors and 13 are web neighbors. So indeed, as you predicted, there is a big imbalance. On the average, I expect to have only a few machine learning friends and a lot of web friends. So one more thing, as you can see, this plus this equals this, because total degree must be sum of machine learning degree and web degree, which we can also check here. Just this plus this equals this, and we have true. Yes, so for each node, adding machine learning and web degree gives me total degree. So again, maybe the question, why do you think I run some check? Does it make sense to even run such code that doesn't do any, additional insight into my data? Why would I write such a line in my code and present it to you in the notebook that is supposed to be used for teaching? Exactly, this is something you must do. This function is maybe not super complex, but it's already not so easy. Yeah, it has a pretty complex logic. If something has a pretty complex logic, golden rule is never move forward unless you had made sure that you got what you expected. And this is exactly this check. If this check passes, I'm pretty sure my function is okay. If it failed, I'm sure it's not. Because, okay. So now we can check what is the mean degree of machine learning and web developer, but conditional on whether I am a machine learning or web developer. So this will be a first insight to our original question. And this is kind of a loop that you could write if you didn't have any better functions to do this. So I iterate developer type to be either 0 or 1, and column that is inspected to be either degree ML or degree web. So I'm iterating on 2 dimensions. And what I will print developer type. I will print whether I am looking at web or machine learning friends. And here, what I do, I will calculate the mean of column that is passed. This column is either web of ML, but only if target matches the type. So what I say, I filter out first only machine learning developers and check the mean of their machine learning friends, and so on and so forth. So for example, if my type is 0, so I am a web developer, and I ask how many machine learning friends on average I have, I see 1.5. So in fact, not much less than the total average. But if I ask, okay, but how many web friends do you have? I have 16. Yes, so many more than machine learning friends. But for web, for machine learners, it is 4 and 4.5. So you can see, and this is not something you expected, or at least not what we have initially said. If I am a machine learning developer, I expect to have more friends who are web developers than who are machine learning developers. But now we know why. Why is it so? Because there are many more web developers than machine learning developers. But is it a bad news? Not really, because we can see that still, if I change here from 0 to 1, I have 3 times more machine learning friends and 4 times less web friends. So we learned here that it's not the absolute number that matters, but actually relative number, because I want to see if I can differentiate by this value. And the answer is indeed those two numbers differentiate me between the groups, but it's not their absolute value that is important, but relative value. Yeah, so it's really important, especially this is a very common case in unbalanced data, that you need to look at the relative values, not just at absolute values, because absolute values might be misleading because of unbalanced classes. Is it clear? Okay. And I hope it's interesting. It was interesting for me when I first analyzed this data set. Okay, but can we do it simpler, in a simpler way? And here you might not remember everything from the first date, but we already showed this, that you can do this pretty conveniently with functions from data frames. So first I'm chaining operations because I will want to do two operations. First, group by my data by this target. So I want to separately analyze machine learners and separately analyze web developers. And then I want to perform a combine operation, so two aggregations. First aggregation, mean of degree of machine learning, and second operation, mean of web degree. Yes? And if I run this operation is run by groups, and in the output, I get a nice data frame where I have for ML target 0 and 1 exactly the same means that we have seen before. Yes, but now I didn't have to write some long cryptic code, but rather in a much more readable way. So even if someone does not know programming, probably you could relatively easily say him, okay, in groups by ML target, so whether this is 0 or 1, calculate me the mean of this web and machine learning developer friends. So we get exactly the same information as before. So the last thing that we will want to do is the following. Okay, we know that indeed relative values are informative in our case, but can we build a predictive model using it? And the answer is yes, we can do this. And we will build such a model using logistic regression. So what is logistic regression? Logistic regression is almost identical to regression you saw yesterday. That was a linear regression, but this time is a regression whose target variable is binary. So I'm either trying to predict whether someone is a machine learner means 1, or someone is web developer means 0. So if it is a binary variable, so what would you guess? What would be the output of prediction using logistic regression? So for example, if I get a result of 0.7, so what, because this will be a number, some real number, I get 0.7. What could it mean if I get 0.7? If in fact I know that either it is 0 or 1. So what could 0.7 mean? Yeah? Yeah, so if it's 0.7, it means it's rather 1 than 0. And again, As we will soon show, actually it's more than that. If I get 0.7, it means that this developer has probability of being machine learning developer of around 0.7 and probability of being web developer of around 0.3. So it can be checked. I will show you in a second how, but indeed it's not just, you know, how strongly I am convinced it is this way or that way, but actually it is more. It is what is the probability. So if I get 0.99, I'm pretty sure it is a machine learning developer. If it's 0.01, I'm pretty sure it is a web developer. So let us first build this logistic regression. So what I do, and this is the formula that you already know. So my ML target is my target variable, and I have two features, degree ML and degree web. And there is one important thing, we already seen this. I am applying the logarithmic transformation to my data. Why do you think I am applying logarithmic? So why I am not building a regression just using raw data, but I am applying logistic transformation to my data, so log transformation. So I am making this right tail of the distribution, you know, squashing it as we just saw in this figure. So this is a very long tail, and I'm just taking logarithm of it. Why do you think I'm doing this? So in order to answer this question, we need to think in the following way. If I take a logarithm of, for example, log 2 times x, what is the value of logarithm of 2 times x? Yeah, log 2 plus log x, which means, now let's revert to our question. So logarithm of 2 times x is logarithm of 2 plus logarithm of x. So now let us think. I tell you that I have 4 friends. First friend has 2 machine learning friends. The second friend has 4 machine learning friends. So this is 2 times more. And now I tell you, I have another pair of friends. One has 1,000 machine learning friends, and the second has 2,000 machine learning friends. Also 2 times more. Now notice, if I didn't take a logarithm, there would be much bigger difference between 1,000 and 2,000 than between 2 and 4. And I don't want it. Why? Because if it's 1,000 or 2,000, probably everyone will say, you know, it doesn't really matter. We are pretty sure this is machine learning developer. Yeah, having 1,000 machine learning developer friends, the likelihood I am web developer anyway is super low. So I do not want to be influenced too much by those super high degree nodes, because most likely they would influence the estimation process a lot, but at the same time this information is not that relevant. While for small degree nodes, actually probably changing from 2 to 4 or 4 to 8 is a lot of information. And I want this information to be inflated to have higher information value. And this is exactly what logarithm gives me. For small values, small differences are important. For large values, I need much larger differences to keep them equally important. So that's why I built this model with logarithmic transformations. And as you can see in Julia, it's very easy to add transformations to the variables in your model just by, writing a transformation function in the formula. So we can see the following. Although both machine learning and web developers have more web friends, but actually those variables are indeed informative in the expected way. This number is significantly positive. So what does it mean that logarithm of decml has significantly positive coefficient? It means that if I see that I have more, I increase the number of my machine learning friends, the probability that I am a machine learner increases. While this other number means the opposite, because this number is negative. It means if I see that I have more web friends, the probability that I am a machine learning developer decreases, which means also that probability that I am a web developer increases. Is it clear? Okay. So now let us make predictions from this model. This is pretty easy. I just use the function predict on model. So I make predictions, and for each developer, I get some number. This number, as we will soon check, is roughly the probability that I am a web or machine learning developer. And how to check it? So first, what we want to check is the following. We want to check if indeed this is the case, that true machine learning developers have relatively high scores, while true web developers have relatively low scores. So those predictions are low for them. So what I do? First, I create a histogram of machine learning developers. So from predict vector, I pick only those elements for which ML target is equal to 1. Is it clear? So I take predict vector, and from this vector, I filter only those elements for which ML target is 1. So I look only at developers who are machine learning developers. And I create a histogram of those predictions, label this histogram as ML, and the histogram should have 20 bins. Yes, clear? Now the second histogram is for web. So here I compare it to 0. I will label it 0, also 20 bins. I need to add a bank here because I want to stack one histogram over the other. Yes, so I want two histograms as layers of the same plot. But I have one problem. If I stack two histograms on one plot, they will overlap. So how to solve it? Well, I solve it quite easily because I say, okay, this second one should be transparent. So alpha is this alpha channel for transparency. So I say web histogram should be transparent. So even if it overlaps with machine learning histogram, I will see them both. And if I run this, well, we already see this, we can see that we have this transparency, and we can see for low predictions, those are mostly web developers. And for high predictions, those are mostly machine learning developers. So we get a first confirmation that indeed our model works, which means it separates machine learning from web developers. Why do you think those bars with web are much taller than bars with ML? What is the reason for the fact that bars in the histogram for ML are, have much lower height than bars for the web? Exactly. There are many more web people. So it's expected that, we have many more very high bars. And even in those bars, blue here are relatively high, but they are low just because there are few such people. Okay, but how can we check if indeed our prediction can be interpreted as probability? Well, this can be done in the following way. So first thing I do, I need to cut my prediction into deciles. What does it mean, deciles? So I cut it into intervals of equal count of values. So for example, here what I mean that the first interval has lowest 10% of the predictions, second interval has second 10% of predictions, and so on and so forth. Finally, last interval has top 10% of predictions. Is it clear? So in a sense, I have cut my population into 10 groups. Each group has increasing value of prediction. So how can I convince myself that indeed my model produces probabilities? Well, the answer is the following. Within those 10 groups, on one hand, I can calculate empirical average of what percentage of machine learning developers I had, because I have those 0, 1 variable, right? So I can calculate its average. Just I have calculated that in total, in the whole population, there were 25% of them. So I also can calculate this in each group, right? But if my prediction is a probability, this means that if I calculate the average of this prediction, I should get a similar number. Because if it's a probability, or if I average over many values, I should get the similar number. So what I see that I can check if indeed my predictions can be roughly interpreted at probabilities if in each bin my prediction is roughly comparable to my empirical data. Yes, and now we will do exactly this operation. So I will call a data frame that will contain the result diagnostic. Why diagnostic? Because I am diagnosing if indeed I get probabilities from my model. So again, I do two operations. First, I take this classes data frames as input, group it by decile. So I will perform all my operation per each decile, and within each decile, I calculate two means. First, mean of ML target, so of this 0, 1 variable, and the second, mean of predictions. And I want them to be similar, right? If they are similar, then I say my model is good and indeed produces probabilities. Is it clear? Yeah, okay. I can repeat it one more time and even maybe draw it on a blackboard. So I say the following. I have my true labels. Those are true labels. 0, 0, 1, 0, 1, 1. And now I get predictions from my model. And my predictions assume they are be 0.2, 0.3, 0.4, 0.5, 0.6, and 0.7. And now I say the following. I'm grouping those predictions by in groups. So for this size, it would be too much writing. So I say, okay, I group those predictions into two groups. This is group low probabilities, and this is group high probabilities. And I say the following. How do I say that those probabilities are a good approximation of those values? Well, if average of this within group is similar to this average, and average in this group is similar to this. So now I calculated. Here the average is 1/3, and here the average is 0.3. Here the average is 2/3, and here the average is 0.6. So I say, okay, 0.3 is similar to 1/3, and 2/3 is similar to 0.6. So I say, okay, well calibrated. But if I had the situation that I had the reverse, here I had 0 and here I had 1, then I would have 2/3 here and 1/3 here, and you would tell me, oh, no, your model is not good. Clear? Okay. So now I run this operation. I run this operation on my data. And we know that we have those 10 deciles, yes, from lowest probabilities to highest probabilities. I have true mean probability from data, and here this mean from predictions. Okay, it seems they are similar, but it's not that easy to see it. I would really need to, in detail look at the data. If you have such huge tables, it's much better to create plots. So let's create plots of this data. So I make a plot of my data where first I plot this probability ML, so this observed probability. That's why I label it observed. Peaks are from 1 to 10. Label is decile because I am in deciles, and Y label is this probability because this is computed probability. And then I add a second plot, this probability computed from predictions. And I label it as predicted. And now I, see both lines on the same plot. And now I could say, okay, there are some differences, but not that huge. In general, this model looks good, right? There are no huge differences between empirical data and predictions. So the conclusion is that this model is well calibrated, which means that indeed I can say that roughly the prediction from this model can be interpreted as probability of being either web developer or machine learning developer. So to wrap up our course from today. So what we have learned? We have learned the following. First of all, how to load and work with graph data. Second thing, what we have learned how to do analysis of properties of graphs. And while learning it, we learned how to do simulation in Julia, how to do numeric computing in Julia, and how Google made such big money. And why celebrities also get a lot of money. So those are those graph properties. So it's worth to study graphs. And the last thing is that if you have graph data, you can pretty easily leverage the graph information in building predictive models. And we have learned how to build a predictive model using binary target variable, and how to check whether this model indeed gives a good prediction, so separates zeros from ones, and how to check if indeed the predictions from this model can be interpreted as probabilities. So pretty much for 2 hours of work. So I hope you are not exhausted because there was a lot of material covered, but I hope you found it interesting and useful. And as usual, if you have any questions, please just reach out to us. Tomorrow we are here also, so you can also come back tomorrow if you have any questions, because today we know that the material, every day you probably see the material is a bit more advanced than the previous day. So if you have any questions tomorrow, please come back to us tomorrow. And last thing, just as a reminder, if someone would want to take this course to be graded, tomorrow at the end of the session, we will give the additional exercises as a homework, and this homework should be handed back to Przemysław. There was an email given, to which email you have 1 week for this homework. If you send it back, it will be graded, and you can get a credit at MIT for this course. So this is all for today. Thank you very much, and I hope it was interesting, and I invite you to join us tomorrow. Thank you.